Hello everyone. I will start my presentation with reactive systems that focus on high availability with Lerna. Let me introduce myself first. My name is Yugo Maaede and Twitter ID is Yugo. I work for Japanese System Integrator TIS. I'm the product owner of an OSS product called Lerna, which I will talk about today. A little while ago, I translated Akka in Action into Japanese. The title of Japan version is Akka Practical Bible. Let's get down to business. First, I would like to talk about motivation in our efforts. High availability and high throughput are often required as non-functional requirements for mission-critical systems that we develop. But these are a headache for us. We have two options. They are using highly available servers or building distributed systems. Highly available servers are costly, and demand for high throughput is more expensive and puts a strain on service profits. On the other hand, building a scalable distributed systems in the cloud can keep costs down, but the system is very complex and difficult to build. So, one of mechanisms that can accomplish high availability and high throughput quickly with low cost is our motivation. Our solution is to build a reactive system using Akka. Responsive, elastic, and resilience are essential to us and are made possible by Akka, which implements message-driven. The architecture implements Akka's Akka model with stateful application to achieve high throughput and distributed system using Akka cluster. Our daemons race condition is limiting factor in throughput. To avoid this, we persist events to the distributed database with event sourcing. Then, to achieve flexible query processing for that data, we adapt the CQRS model to reflect the data in the query-side database asynchronously. With this architecture, we have successfully launched the mission-critical services. To speed up building this kind of system, we refined the architecture and trained engineers while repeatedly building mission-critical systems by creating a repository for the result. We call this repository Lerna and use it to build mission-critical services. Therefore, we have released Lerna as OSS. Lerna is a software stack for building reactive systems focused on high availability. We have developed libraries, developer guide, reference code, learning content, and other things for building a high available system using Akka and publish them for ready use. Here is an image of using Lerna. If you have a virtual machine, execute Lerna's Terraform scripts on it. That will install Keeper IBD, HAProxy, Cassandra, and MariaDB on VMs. This is a set of middleware for high availability. Next, deploy the Akka application on it. The application is built from the supplied guitar-rate template. Developers learn from the learning content and develop using convenient libraries. Reference code is also offered as a sample application to accelerate its development. So, what level of high availability does Lerna accomplish? 5.9, 6.9, we express Lerna's availability numerically. I think it is probably a general calculation formula. Get availability from MTBF and MTTR. As cloud application become mainstream, we often hear the word design for failure, but I haven't seen much quantifying of which designs are more resistant to failure. It is important to minimize the impact on your users. Let's go back to the question. It is clear that MTTR should be minimized to maximize availability. Next, availability also depends on the key type of application and operating environment. So we made the following assumption. We develop a payment application on AWS. It uses a CQRS plus event sourcing architecture. The command-side payment API does not update the RDMS, but persist event into Cassandra, the command-side data store. The grants of payment detail can be processed on the query side, since this use case requires higher availability on the command side than on the query side. The measurement target is the API on the command side. Continue to send 150 TPS requests using Gatling. Under these conditions, we cause a simulated system failure. When a server at each layer fails, the MTTR for its failure is defined as a period during which even one user cannot use the service. When then assume that each server fails once a year, multiply the number of servers by the impact of the failure, the effect of the failure is the percentage of users that are unavailable when a server fails. The annual downtime is the sum of the MTTR for each failure layer. Now, the measurement results are as follows. As you can see, all layers recovered within 10 seconds. Here are 3 key points. To minimize the scope of impact, disconnect it immediately and continue processing on the remaining server instead of recovering the failed server. Don't worry, our layers have a scalable architecture, so it is enough for us to slowly start a new server and return to its original state. Which layer was the most difficult to recover in less than 10 seconds? It is application layer. An application using a cluster sharding has only one entity in the cluster. In addition, the feature called a split brain resolver enables recovery from network partition safety without causing split brain. But we couldn't recover in 10 seconds. So we have developed entity replication, which does not lose consistency and recovers within 10 seconds. We implement Raft algorithm. This algorithm is that entities are replicated to multi-nodes and the elected reader takes care of them. I'm going to show you a little demonstration. I send a request from the window at the bottom left. I'm getting a normal response with the green. The server side processes on 3 nodes and can be seen in the top 3 windows. The reader is node 2. It is a process on node 2. Node 2 stops processing and the request results in an error. As a result, the red characters are displayed in the lower left window. The reader has moved to node 3. And the request log quickly returns to green. It takes about 2 seconds. This demonstration is available on GitHub along with the library. So, how many seconds of annual downtime have we had? 21.18 seconds. With less than 31 seconds of annual downtime, we achieved 99.9999% availability. Let's also touch on Elastic. Availability was tested under a load of 150 TPS, but Lerna could scale out and even achieve 1000 TPS with the addition of nodes. But of course, this is not the limit, because Lerna is elastic. However, the response time, even with 1000 TPS, payment transaction responded with an average of 100 milliseconds. Lerna is responsive. You can read more about Lerna's availability and performance in this article, and since Lerna is OSS, it's available to anyone at this link. Also check out the TI's technology site FinTerm. In addition to Lerna, we also publish a lot of tools and documentation that we've created from our mission-critical service and innovative development experience. Again, I hope that FinTerm can help you. Finally, its conclusion. If you are building mission-critical systems in a cloud, you should use Lerna. That's all for my presentation. Thank you very much.